Oh, that's the wrong screen. That's so funny. Hi everyone. Welcome to Thursday, sorry, of week 2. Um, Today we're going to finish off just a little bit on time complexity. Just like the last tiny bit that we didn't get to do on Tuesday. And then we're going to be talking about ADTs and stuff. I think just a heads up for those here live today. I don't want this to go till 4 o'clock because I have a meeting at 4, like go over 4 o'clock. But if it's just a matter of 10 minutes to really finish off the topic, we might run just a little bit over today. We can make it up in a later week. But it's all recorded anyway. That's just worst case, just as a heads up. Just because I don't want people, when you get anxious, like it's like 5 minutes till the end of the lecture and they aren't shutting up. So, and sorry about being late. I had a meeting with work in the city and I had to leave the meeting early to come back here, and it's raining and trains and everything else. So I kind of ran in the door at like 1:57. But on the plus side, I've started adding the date to the lecture link because I know that's a yes, I get what it's like. You're all sitting there clicking it being like, when is he going to arbitrarily update it? That's really frustrating. So the date will help you figure out whether to click the link or not, or whether to just refresh the page. Generally, I try and do it like 5 or 10 minutes before. But let's get into the tail end of performance analysis. Coldest day in Sydney today, really? Damn. It was cold. I ride a motorcycle and I rode without gloves because when it's raining, sometimes it's better to ride without gloves than get the gloves wet, if that makes sense. And my fingers felt like they were falling off by the end of it. So that would make sense if it is cold. So where we got to at the end of the last lecture was we kind of got to the end of big O notation. We talked about programs and literal timing and then general complexity, and then we got into big O notation. And where we kind of left it, which I really want to just chat about a little bit, it's hot as hell in India, that sucks, is analyzing a search program, right? So what we want to talk about is like if you have a list of numbers, and we're gonna write this up really quickly together because I think it's really interesting. So I've got this folder here called search. And I've got this file here called search.c, which is a bit more of a complicated search. It's got a couple of searches here in it. And I'm just going to open this. I really like Sublime text editor. It's somewhere between gedit and VS Code. So if you're using VS Code, I'm basically a dinosaur to you. And that's okay. We're all allowed to be a little bit different. But what I want to show you is essentially like a couple of different ways to search through a list of numbers. So I've got this program here called search.c, and I'm just going to comment out the part of it that I don't care about for now, right? We're just going to keep it really simple. Now, I have a main function up the top here, which basically it creates an array of ints. Up to 100,000 ints, and then we have a counter and a scanf, and essentially just like the other programs, we're reading them in from the command line, right? And then at the what we're doing is then we're trying to see whether a number is actually in that list or not. Now, just for simplicity, I've put the number we're looking for as a hash define up here. So what we're going to do is we're going to read in a list of numbers like this random 100. And we're going to essentially see if there's this 18875 number in there. Or we might start off with a simple number like 10. And we're doing that by creating a search function here, which takes in an array of numbers. It takes in the size of that array, and it takes in the needle or the number that we're looking for. And it tells us whether it was found or not. So it simply returns true or false. And this is a very first year, first term function where essentially you have an array, you look through it, you check for each value whether it's the number you're looking for, and if you find it, you return true. So we're essentially just trying to see whether something exists in an array or not, in a list of numbers. Pretty straightforward program. We can try and compile and run it together, right? We can use our wall where I leave the big O out for now, and we'll compile it, search.c, and then we will run it, except we need to give it a bunch of numbers. Now I could give it some numbers just by typing them into standard input. I could go 4, 5, 2, 4, 9, 10, 4. I could press Control D, Sorry, I do this sometimes. If you ever see me write G++, it's just GCC. I'm sorry, I will try not to do it. Thanks for reminding me. But yeah, this is the same thing. So it should be GCC. And when you click Control D, it says we found it, because what it did was it went through 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers, right? And it found the one you're looking for. Now the big question, I'll just compile this properly so that you can see. And we can do it with a set of numbers as well, right? We've got all our random 1000.txt files from the other ones. So you can see that the number 10 is inside of our 100,000 random numbers, right? It does exist there. And, you know, it's a pretty quick, sorry, 100,000. There we go. Not found in that one. And you can see it's a pretty quick program. It takes 0.024 seconds. But the big question here is, what's the time complexity of this program? Right? I'm sure someone could tell me pretty quickly. What's the big O notation of it based on what we talked about in the last lecture? It's linear time, right? It's ON. So, and the reason for that is because, you know, you look at this for loop here and you're going to loop through this in the worst case n times. And these operations here are just primitive operations that are trivial, right? So they get totally kind of ignored. They're like those constant time operations. So this is an ON algorithm because in the worst or average case, you're going to loop through it n times. And you could actually kind of write this out. So for like linear search, the best case is going to be what, O1? Because it's right at the front of the list. So if the number you're looking for is right at the front, then no matter how big the list is, no matter how big the n input is, it's going to be instant, right? So it doesn't vary based on the input. The average case is a bit more interesting, and the worst case is ON, because you have to go through n numbers to figure out whether it's actually in the list or not. Now the average case is really interesting, right? Because the average case here is going to be it in the middle, right? So if the number's square in the middle. And in that case, you could say that the average cases are half times n, or like 0.5 times n, because it's half of n, right? Like there's a list of n numbers, and the average case is that it's in the middle. So it's a half n, but as we talked about on Tuesday, we ignore leading coefficients, so you actually end up saying that the big O notation for time complexity of the average case is ON anyway. So what you would end up with, which is a little bit of a bit of a mind screw, so even though in reality it is actually a little bit quicker average, you still write it as ON, because again, as we've said, we ignore those coefficients because we're looking at the tendency of the algorithm as it scales. Yes, and I think people have answered some questions in the chat. So that's linear search. Now that's all great, but the problem is that trying to find whether a number or a value is in a list is an extremely kind of common activity, right? You might have a billion items. I think I think I talked about this in a different course, but it's like, you know, you might have every single person's tax file number in Australia, or every single person's driver's license, and you're trying to look up, you know, whether it still exists, whether it's still valid. You're trying to find the entry, you're trying to search for it, and you don't want to take a million operations every time you do that, like, because again, if a million operations takes you about 0.05 seconds, or 0.005, whichever one it is, then if you have to do this for like 200,000 people, that's going to take a long time. That's going to take minutes upon minutes upon minutes. So what we want to do is we want to find a faster way to search a list of numbers, right? And this is where we get into this topic of a binary search. So what I have here on the left is our standard linear search that we've been looking at. And on the right here, I have a binary search which does the exact same thing. It tries to search for a number in an array, and then there's the number you're looking for. So you take the array, you take the number you're looking for, and you try and look for it. But the interesting thing about a binary search is that in a lot of ways, it's actually one of the most intuitive ways of searching, because all of us have played this game as children or adults, where I say to you, I'm thinking of a number between 1 and 100. What is the number? And then you start guessing, you know, and and I'll tell you whether it's higher or lower. So I'm like, I'm thinking of a number between 1 and 100. You give me an answer, I'll tell you whether it's higher or lower, and we see how quickly you can guess it, right? Now, if you're a smart person, which all of you are, the first number you're going to give is going to be 50, because it totally, you know, separates, it gives you the highest information gain after the decision. So you know that if they say lower, it's only 50 left, and if you say higher, it's only 50. And then if they say, oh, it's higher than 50, you go straight to like 75, right? And then they say lower, and then you forget how to do math, and you're like 62 or 63. And then they say lower, and you go to like 57, and you kind of like, you keep halving it, right? You keep halving it in. And that's what a binary search is. So instead of just iterating through every single number in an array, we instead play this game with numbers in a computer. Now, as people on the chat have said, or at least one person has said, one thing about a binary search, though, is that the numbers have to be sorted, right? Because when someone says, when you pick the middle number, like 50, and someone says, oh, it's in the first half, you need to know that all those numbers are lower, right? Because you can't really play that game if all the numbers are randomly assorted. They need to be like literally sorted from 1 to 100 or whatever numbers exist. So that's one caveat of this, which we're going to loop back to at the end to chat about. But essentially, a binary search searches on numbers really quick if they're already in sorted order. Now, we're not going to talk about the algorithm too much just because of the time we have today, and you can kind of look at it and work through it yourself, but we will look at the code. But essentially, it's pretty straightforward in terms of like, if you think about that game, counting from, I'm guessing of a number between 1 and 100, you kind of start off with a left bound and a right bound, right? You know it's going to be between 0 and 100. That's where the game starts. So your guess is going to be the midpoint of those two things, right? So I'm guessing between 0 and 100. The midpoint's 50. So that's the first guess I make, right? And then after that, I'm essentially going through this cycle, this repeated cycle, where if the number I'm guessing is less than the number I'm looking for, then I kind of go higher, right? And if it's greater than the number I'm looking for, then I kind of go lower. And I essentially just keep adjusting my bounds, right? Like if you say 50 and they say it's higher, you go, okay, well, it's between 50 and 100. Then you guess 75. And they say it's lower, you go, oh, now it's between 50 and 75. So you're essentially slowly collapsing your bounds until you either find the number or until you only have one number left, which like is the number. Or in a case of a binary search, it might also just not be there, right? It could not be there. But let's not get too caught up in the pseudocode yet, because the rest of what we're talking about are it'll just be easier to look at in the code. So what I've actually got here is, instead of this search function, I've actually got myself a second search function here, which is a binary search. Now, what's kind of notable about this one is this function is actually written recursively. So in this function, our search actually calls binary search, and the way a recursive binary search works is it essentially just keeps calling itself with different bounds, right? Because if I draw this in my good old friend Microsoft Paint, you kind of do your first search for a number where, say you're looking for the number 66, right? You look for 66 between the 0th and the 100th element, and you look for 66. And then someone says, oh, it's actually in the first half. Okay, so now you do another search between 0 and 50 for the number 66. Now, where the example that I provided breaks down here is that when I tell you I'm guessing of a number between 1 and 100, I'm literally actually telling you that all the numbers are like 0, 1, 2, 3, 4, 5, 6, 7, like 8, 9, 10, all the way up to 100. Whereas in this example with the binary search, the left and right bound actually represent the index of the array. So the actual array itself might be something like, 1, 22, 33, 34, 35, 39, 42, etc. Like this might be like a whole bunch of numbers, 100 numbers though, from like 1 all the way up to like, 765, 888, 987, and then the end. So in this case here, what we're saying is we're going to look for between the 0th and 100 number for 66, and if the result of that search is like, actually it's lower, then what we do is we search in like a smaller bound, like this. And then we keep doing that again, and we can essentially keep recycling the same function because the logic keeps applying. Because we bigger bound, smaller bound, smaller bound, smaller bound, smaller bound, we just keep going down like that, which is pretty cool. So the actual implementation of this we've got here. And the way it works is that you have your this is a pattern you see with recursive functions where you have your kind of starting function for the recursion. You don't always have to have this, though I've written it here just for like simplicity, where you say I'm going to call binary search with my array, with the left and the right bound, right? So the first index and the last index, and then I'm going to give it the number that I'm looking for. And then all the binary search does is it simply keeps going through it. I think this function is missing something, but that's okay. This function should be returning true and false, which is just my bad, I think. I think this should be return true. I'm not going to touch it because I think I tested it and it worked fine, even though it probably shouldn't have. So all we're really doing here is we got the left and the right bound. We're going to find the midpoint, we're going to guess the midpoint, and if it's not it, we look left, and if it is it, we look right. Right? Because since we know it's sorted, then if it's not the exact midpoint, we know that everything to the left of it's smaller, and we have to keep looking. And again, I know some of you are looking at this and you're like brain melting, but just for the sake of time, I can't really spend like kind of 20 minutes really stepping through this one. We kind of just have to be selective. So if this one is giving you grief, I'd suggest kind of just going away, or even more, some of your tutors will be talking about it in the tutorial and can give it some more time. So what should actually probably be happening here is this. I think this function was just a little bit whack, but that's okay. The general gist of it's the more important part, because there are different implementations of this too. Like there are iterative solutions for this. Like it doesn't have to be recursive. Like it can be totally iterative as well. But we have our binary search, and we can try and call this, and it probably won't compile because I poked it now. So knowing my luck, it not found. Okay, so similar thing. It's the same program we were running before, and we're looking for the number 10. But what you've noticed here is I've just tried to run it with my random 100,000 numbers. And what do we know about a binary search is that it has to work with sorted numbers. So I have my sorted numbers here, right, from 0 to whatever. And I'm going to say look for the number 170 or 102. Let's do that one. So the number I'm going to be looking for is 102, and we're going to pass in our sorted 100 into the program. So I compile it, I'm going to run it, I'm going to pass in sorted 100. And it says that it's found. Now what I'll show you here as well with the binary search is let's actually have a look at all of the numbers it looked for. So inside of my recursive function here, I'm actually just going to print out checking and then a number, and then we can actually kind of see the flow of how it moves through this. So if I recompile this one and run it, you can actually see how it's searching. So if I open sorted 100 here, you see the first number it searched for was 411, which is line 47, which as you can see is pretty much smack in the middle, right? So it starts in the dead middle. And then the number we're looking for, which was 102, is actually smaller. So it's like, oh, 411 wasn't it. And 411's bigger than 102, so we better go look in the lower half. So then it picks the next middle number, which is what, about 23? 205, so the next one it checks is 205. And it says, oh, 205 is still bigger than 102. So I better halve that again. And then it jumps halfway to 95. It was really close, but it missed it. Then it says, oh, 95 is a bit too small, so then it'll start looking now between 95 and 205. Right, so at this point here, these are the bounds. So it'll find the midpoint again, which is 149. So that's a new upper bound. But it couldn't find it there. It says 149 is bigger than 102. So again, it halves it one more time. This is the new upper bound. 131, and you get the point. It keeps going, and then it eventually finds 102. Jay says, do we round up or down when we're finding the middle index, or does it not matter? It doesn't really matter. I don't know if there's like a particular like aggressive convention. Generally, it'll probably be down because of how integers floor. Like when you divide two integers and you try and capture it as an integer, it goes down by default. But generally, you could probably write an algorithm where it goes up perfectly fine. You just have to check it and test it, because these kinds of algorithms are really prone to subtle bugs like fence post errors and other things. So you just have to kind of be careful with it. But again, this isn't the only solution. You can Google solutions to this on the internet. You'll see a bunch of like iterative solutions and other things again. Autumnal says, can you show it with the print line with a number not in the list? Sure. So if I now look for a number that's like, say, 111, which isn't in the list, and then what I'm also going to do is I'm going to print out the index here as well, just for you, so it's real easy. So I'll say like nums the index equals that. So we'll print out the index we're searching and then the value at that index, so you can kind of see it a bit more. So now when I run it, you can see that it checks the 46th index, the 22nd index, the 10th, the 16th, and it's basically just like jiggling around till it finds what it wants in the middle. Which is pretty cool. So you can see to search 100 numbers here, we only had to look through 1, 2, 3, 4, 5, 6, 7, 8, which is pretty sick. And let's see what happens if we have to look through 1,000 numbers. See, for 1,000 numbers here, we only had to look through 1, 2, 3, 4, 5, 6, 7, 8, 9. For 10,000 numbers, we only had to look through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then when we look through more, it's like not actually having to search through many more. Now, why is it not found? All of the different sorted lists are actually totally different randomly generated lists, just FYI. They're not like the same list cut down, so that's why it's found and not found. And Jay says, why is it 46 first if we have 100 numbers? That's actually a great question, Jay. For some reason, my program only has 93 numbers. I couldn't tell you why. It's probably because I'm stupid. This one seems to have 1,000. So I'm not sure why 100. I've probably, when I've sorted it, I've probably removed duplicates. That's probably what I've done by accident when I was like trying to clean up this data is, yeah, so I probably just removed duplicates. So the original one probably had 7 duplicates in it. But what's really cool here is that notice how this isn't really growing. So the first question, and one of the last questions we're going to ask here is, what's the time complexity of this program? What's the big O notation of our binary search? So we know from before that our linear search had a best case of O1. And what's our binary search have? It has a best case of O1 as well, because if the number you're searching for is right in the middle of the pack, it's that. We got the average case, which I always like to do last, and we got the worst case. And people are talking here log n. Now, I'm not going to lie, I was never great at maths at uni, and when I first saw this kind of thing as a student, I was like, oh, log n, yeah, sure, that makes total sense. What's a log again? And, if you remember from high school, if you have something that's like 2 to the power of 3 is equal to 8, then log base 2 of 8 equals 3, right? So it's the total opposite kind of thing that's happening. And the reason for that is because each time we do a step in this search, we keep kind of halving it. And if you think about what a 2 to the power of something is, right? Like 2 to the power of 4 or 2 to the power of 5. Anything that's 2 to the power of is essentially saying double it. Get 2, double it, double it, double it, double it, right? That's what, well, technically it doubles 4 times, I think. But like, that's what you're essentially saying is you're like double it, double it, double it, double it. That's what an exponential is base 2, is you're always doubling the 2. So therefore a log 2, log to the base 2 here, is essentially saying halving it, halving it, halving it, halving it. So if you have a kind of data set or a set of numbers you're working with where you are simply halving it each time, that's your operation as you start with this much data, and then the next operation you have this much data and this much data until you get down to 1, is it's the opposite of an exponential, which is a log. And you can actually see this pretty clearly because, if you have like, we could figure this out too. If we said, what's log 2 of 10,000? It says that it's 13. And what's really interesting about that is that when we searched 10,000 numbers, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Worst case, because the number wasn't found. It could be quicker, of course. So log 2 here is saying, how many powers of 2, right? Like 2 to the power of what gives you 10,000? And the answer is 13, roughly, right? Like it's about 13. It's probably like 13.1 or something, or 19.9. But yeah, so it's like, that's why it's log 2, because that n there is 13. Caleb said because it exponentially halves the set. Yeah, It's like the exponential in reverse. So that's why its worst case is log n, and similarly its average case, I guess, would be half log n or something, or log of a half n. Or the point is, most average cases end up being worst cases, because most average cases are simply like a half. I'm no mathematician, so I don't. It's not going to be a half n. It'll be something like this, right? I don't know. Could Google it. Average case binary search. I probably already Googled it and put it on a slide somewhere. Yeah. Average case is log n as well. Okay, cool. So nothing crazy. Yeah, so a log graph as well. Like if you look at a log, they're the headphones I tried to buy. Whoops. Oh yeah. Okay, so if you look at a log graph, it does, as someone said, have the opposite behavior of an exponential, where it kind of rockets up really quick and then it tapers off, as opposed to an exponential, which starts slow and then rockets up, right? So that's also why you see that when we sort like 100 numbers, we actually have to do like 8 checks, but then when we do literally 100 times more than that, we only have 13. Like, it's not even double the time. So logarithmic functions are really powerful in terms of time complexities, because they, for large data sets, they can grow horrifically large, and it's still like not that bad to search through. Now, I really want to finish this lecture off so we don't spend all day on it, even though it's super interesting, and this, you could probably see why we want to talk about it. But the last thing I want to talk about in terms of binary search is this notion of amortisation. I don't think Googling this definition is very helpful. It makes sense, and there's lots of different ways people explain it. The most common way you'll see it as being described as amortized analysis. But the simple way I tend to try and describe it to students is, in a practical sense, if you were to ask someone, you know, can you amortize this at all? In a programming sense, you're kind of saying, can we do some work up front to reduce the work later on? Okay, and why I love this binary search comparison here is because we know that the average case of binary search is log n, and the worst case is log n. But here's the problem with binary search, is that the numbers need to be sorted. So in the real world, you'll often get a list of numbers that aren't sorted. So what that means is to do one binary search, just one. Like, so for random numbers, to do one linear search, you simply need to spend O(n) time, right? That's all. Look through it once. For a binary search, you need to do it n squared to sort. Think about the bubble sort we did before. You need to use n squared to sort it, and then you can use your log n. Right? So like, this is the sorting component, and then this is the searching component. Now, just a reminder too, that n squared is greater than n, which is greater than log n, just in case like that's of concern to anyone. So the binary search looking for a single number on a random list is actually a lot slower. It's really slow because you actually have to sort it first. And that's going to be a huge amount of time. But this is where, like, as computer scientists, you need to start thinking about the context in which you're applying a program. Because again, there is no such thing as a good solution or a bad solution. There's just the appropriate solution or the right solution. So if you were writing a sorting algorithm or a searching algorithm for numbers, you could ask a very simple question. How often are we going to need to search for numbers here? And they might say, oh, probably like 10,000 times a day. And then you say to them, well, is it going to be the same numbers every time? Like, or is there going to be new inputs here? Or is it just like the same set of data? And they'll say, oh, it's the same set of data. So what you know then is that it actually will make sense for you to use a binary search, because you can get that data at the start. You can do one really slow sort on it, which might take, you know, a minute or a few minutes, say, for a large amount of data. And then for the rest of the day, you can do really quick lookups. You know, so like, what are the constraints you're working with in a system? Because sometimes, like, you know, often there are systems that kind of operate during the day and need to work really quick, but they can do things really slowly overnight. You know, so you might be doing all this like prep overnight, like sorting lists and stuff, and then during the day, that means you can look them up really quick. But if the data set you're working with might change all the time, you might just stick with a linear search because it's not worth sorting it, assuming that it's not sorted when you start. So Chewy says, so pretty much you spend more time initially to sort it once, so it's faster in the future if you want to find a number with O log n. Exactly. So the actual initial cost of this is kind of, more. But like, it depends what you're doing again. Like you could give people these examples all day. If you need to catch a flight to Wollongong from Sydney, it's going to be faster to drive. Like sure, a plane's quicker, but like you gotta set up. You gotta do some initial things to get going. But if you're flying to Melbourne, it's going to be quicker to fly because you get the point. I know the plane analogies are a bit overdone, but this is why you're doing this course, is so you can think about these things. So you can think about, oh, well, actually, we can do more work at the start, which I'm just referring to here as amortisation. We can do more work at the start to save on work later, right? And this applies for a lot of things as well. One theme you'll see that we'll come back to a lot in this course is that often there's a lot of caching or amortization you can do where like you can actually use more memory to speed up processing. And in general, you'll see with more algorithms in this course that there's a bit of a seesaw effect between memory and performance. So if you want to write an algorithm that uses less memory, it will tend to take longer. And if you want to speed up an algorithm, you will tend to need to use more memory, right? And sometimes we do that. Sometimes we use more memory at the start to like amortize our program so that over the longer period, over the broad steady state running of it, it's a lot quicker. So that's pretty much it. And then our final table here is a summary of the complexities. So yeah, I already did figure this out, I guess. And also their space complexities. So I just wanted to include the space complexity again because all the algorithms we talked about as part of 2.1 didn't use any extra memory. So no matter how big n got, they didn't use any extra memory. This is ignoring the reading them into that array, by the way. Like, I mean, this is a little bit oversimplified, but the point is the actual search algorithm didn't use any extra memory. Sure, we had to allocate that array to actually read them in from scanf, but that's not the algorithm, right? Like, you have your C program that runs a search algorithm, and that search algorithm didn't use any more memory. So memory's a bit different to time because there's a limit that you can't go over or it will stop working, right? So yes, that's true. A computer can run out of memory, though at the same time, most of the places that you'll actually be implementing algorithms in kind of have implied time limits. Like, yeah, a computer can run faster, like slower, and it won't just like die. But it doesn't mean it can run forever, right? So like when I was working at Microsoft, without getting into it now, the team I was on, we were ingesting data from Azure into like analytics data into Azure, and this is just an internship, by the way. I wasn't like a hotshot there. Is like they were ingesting like 200 gigabytes an hour, and they needed to process that data, right? Not me. I was the dum-dum. They were processing that data, and they had big problems with it being too slow because if they couldn't process that chunk of data within 60 minutes, another chunk of data would come in, and then another chunk every hour on the hour. So time mattered to them a lot, even though it could run forever. If you're trying to process data every 60 minutes that takes 70 minutes to process, you'll eventually lose control of it, right? So time and memory both kind of really do have constraints. Just memory will probably literally crap the computer sometimes. Okay, that's pretty much it. I think we've covered everything. So, sweet. Microsoft take a lot of interns. I'm not kidding. They like take quite a lot of interns from UNSW. And I did a terrible job at that place. I broke things the whole time I was there, and then I fixed them. And then when I left, everything was exactly as I was when I started. So that was my contribution, was to not leave a negative trail. So we're pretty much done for algorithm analysis. Sweet, thank you.